Hi everyone, and welcome to Erik's Electronics Workbench. In this video, we'll be taking a look at a type of capacitor called a safety capacitor. They're also known as X-class and Y-class capacitors. Now you can see on the right-hand side I have two circuit boards removed from a Hewlett-Packard 4195A network and spectrum analyzer. That's the current project on the workbench. But what I'm going to discuss in this video really applies to many types of AC line operated pieces of equipment. It could be everything really from a radio to test gear to shop equipment. Anything that is AC line operated will often have what's called a safety capacitor in it, or maybe several. So let's take a look at these capacitors, how they're used, and why are we replacing them on these circuit boards when they actually still work. I'll explain all of that, so let's get started. Many AC line operated devices need to have some form of filtering on the AC power line, and this can be for several different reasons. So the device may try to generate a lot of RFI or radio frequency interference internally due to a switch mode or switching power supply, which operates at a very high frequency. And that interference or RFI can emit or radiate out on the AC line if it's not properly filtered. Or the device may be very susceptible to outside interference coming in on the AC line and need to have that type of interference filtered out. So for whatever the reason of this filtering, we're using capacitors, sometimes one, sometimes several capacitors, and they're connected directly to the AC line. Now, anytime you have a capacitor that's connected directly to the AC line, a safety issue arises. If that capacitor fails, it can cause a fire hazard or it can cause a shock hazard. So let's take a look at the two different ways capacitors are actually connected to the AC line. So right here we can see there's a line and neutral on a 120 volt system, and we have a capacitor connected across the line. All right. Now if this is a 220 or 240 volt system, this would be a line and a line. On a 120 system, it's line and neutral. So this is referred to as across the line. Down here we have line and neutral. If it was a 220 or 240 volt system, again it would be line and line, but a 120 it's line and neutral. And here we have a capacitor connected from one of the AC lines, in this case neutral, to chassis ground or earth ground. All right. Now up here, if this capacitor were to fail, it can cause a fire hazard. And the reason is because it's directly across the AC line. So a failure here can be a direct short, and a direct short circuit, of course, can cause excessive current flow, can cause a lot of heat, and then in turn a fire hazard. Now down here, this capacitor can result in a shock hazard if it were to fail. If this capacitor fails to a short circuit, this AC line can connect to earth ground or chassis ground. And if the device is a metal frame that the operator is touching, then of course there's a shock hazard. Now, neutral and earth are often at the same potential, and in fact in your breaker panel you'll find the neutral and earth ground do tie to the same point. However, if there's a miswire in the wiring at your outlet or in the house or the building that the device is being used in, and this is the line and this is the neutral, then here we have a hot AC line that could potentially be connected to the chassis or earth ground. So again, that's definitely causing a shock hazard. So the term safety capacitor is referring to how the capacitor is designed to fail if there's a problem, and it's designed to fail in a safe way. So this capacitor up here is known as an X-class capacitor, all right? And this capacitor is known as a Y-class capacitor. And there are subclasses, which I'll show in just a moment, related to different voltages that the capacitors are able to withstand. Now, X-class capacitors are designed to go across the line, and if they fail, one of their features is that they're self-extinguishing. So if they were to try and catch on fire, they self-extinguish or the fire goes out. Y-class capacitors, if they fail, they're designed to fail in an open mode, all right? So they basically become an open circuit, disconnecting this line from the chassis or the ground connection. All right, so in this case, you lose the capacitance and the filtering ability, but you save the person that's using the device because you don't have that shock hazard. When this capacitor up here fails, oftentimes a breaker or a fuse will trip because this will become a short circuit up here. Now there are capacitors that are both X class and Y class rated, and they combine both classes into one capacitor. The capacitors that I'll be showing in the example here are either X class or Y class. They're not both in one capacitor. Now this circuit board that I have sitting here is out of the HP 4195A network and spectrum analyzer, and it's part of the switching power supply in that device. So we can see over here there's an X2 rated capacitor. So this is an X class capacitor and it's subclass number 2, all right? And this is a 0.6 microfarad capacitor. So this capacitor is connected directly across the AC line. So it would be connected as this is shown right here. This capacitor right here is a 0.015 microfarad capacitor, and it's a Y-class capacitor, actually a Y2, all right? So this capacitor is connected like this is shown down here. This is not across the AC line. It is from one side of the AC line to a chassis ground or a shield of some sort within the device. Now, as I mentioned, there's subclasses on the capacitors. Put this out of the way, and we can see here. Zoom the camera in just a little closer, make it a little easier to see. So we can see there's X1, X2, and X3, and then Y1, Y2, Y3, and Y4. So X2 and Y2 are the most common types of safety capacitors. And the capacitors that I'll be using in this example here are either X2 rated or Y2 rated. Now you can see the voltage rating increases as we go from the bottom up, so from Y4 up to Y1 or from X3 up to X1. The voltage rating that the device is able to tolerate increases as the class number gets smaller. So when the manufacturer made these capacitors, they assumed that if the capacitor were to fail, that failure would originate because of something like an overvoltage condition or a voltage spike, and that would damage the structure of the capacitor internally, and then they would fail, and they would fail in their designed way, you know, in the safe way that they're made to do so. What the manufacturer didn't assume was going to happen is that the housing or the case of the capacitor would begin to deteriorate. And that's actually exactly what's happening on these capacitors. So if you have 30 or 40-year-old equipment and you look at the capacitors on the board and you see this RIFA name, R-I-F-A, those capacitors are becoming little ticking time bombs on the circuit boards. And what's happening is these capacitors are getting little hairline cracks in the housing. And the hairline cracks allow moisture that's just naturally in the air, you know, the humidity that's in the air. It works its way into the capacitor, the internal structure, and just wreaks havoc on the internal portion of the capacitor, and it ultimately fails, and it really does so in a spectacular way. So if you see this RIFA name on a capacitor or multiple capacitors, you can see there's another one right here, they have got to go. Now I have an HP 6269B DC power supply, and it recently let out a big cloud of smoke, and of course when I opened it up on the pre-regulator circuit board, guess what? 3 of these RIFAs in there. One of them had split completely down the top and looked like a chunk of charcoal, and the others weren't far behind. They had cracks in them as well. Now this other circuit board that right here, we can see it has 2 additional RIFA capacitors right here, so I'll be replacing those, and again the 2 that are on this circuit board here. Now for the replacements, I actually use the RIFA brand. I've had very good luck with them in modern versions of their capacitor. So here's 2 examples right here. So these are new production. They're not 30 or 40-year-old capacitors, of course. They're brand new, recently made. And over the last 20-some years of replacing these RIFA capacitors, I've had no replacements that I've installed ever fail or even develop a crack. And I've gone back and looked at capacitors that I've installed and have had no issue whatsoever with the replacements having any problems. So I've continued to use the RIFA brand. It makes it very easy because they drop right in on the board. The lead spacing is the same, they go right in. And they really seem to perform fine. They seem to be a good capacitor otherwise. They tolerate voltage spikes. They meet the ratings that they're supposed to. And again, on the modern version of what they're producing, I've had no issues whatsoever. Now, there are other manufacturers of safety capacitors, and the other manufacturers I'm not aware of having cracking or issues with the housing. It really just seems to be these RIFA capacitors, and really in the older type equipment. So again, going back 30 or 40 some years. So the next thing we'll do is get the desoldering tool prepared, and we'll replace these capacitors. Okay, we're ready to replace the 4 safety capacitors with the new components. So there's 2 on this circuit board and then 2 on this other circuit board over here. Now, if you're following along on a project like this, please know you do so at your own risk. So please know the safety precautions involved when using desoldering and soldering equipment. Use appropriate eye protection and so on. And also know the safety precautions around the AC line voltages. Any circuit boards that you're doing work on like this are completely disconnected from any AC power. And then when you do go to test the circuit boards with the new components, know the safety precautions around those AC line voltages, and just be safe, be cautious. So again, you do so at your own risk. So to do the desoldering, I'll be using this Hakko FR301 desoldering tool. All right, so it has a vacuum pump in here, and it basically is able to suck the solder up through the tool. The tip is hollow and fits over the component lead where it comes through the back side of the board, and it just vacuums out the solder around that lead, and basically the component will fall off the board. It's just that simple. So this is a double-sided circuit board. Double-sided boards with plated through holes don't take very well to desoldering with a soldering braid or a soldering wick. You'll have much better luck using a vacuum desoldering tool. So you just come in here like so, heat the part, so, and that one just fell out on the other side as soon as it was heated up. Didn't even need to desolder that. I'll vacuum this like so. Put that a little bit more. That cleared out that hole, so you can see. I think you can probably see the light through where that was. It just went right about there. So the old component falls right off the board. So it's just that simple. And we'll take the new capacitor, which we have here. All right. And you can see that just fits perfectly in there. It's exactly the same lead spacing, just a direct replacement. Exactly the same specs as this old original capacitor. So the replacement is really very straightforward. Just give the leads a slight bend to the side like so. You want the component to sit flush with the circuit board, all right? You don't want the component standing, or the capacitor standing out this way from the board, so it's completely down, flush against the board, all right? And I'll grab my soldering tool here. All right, I have my soldering iron ready, and we'll just come in like so. So when you're making a solder connection, you want to heat the joint, the component lead and the pad on the circuit board. And then just add some solder like so. The plated through holes, you need to make sure that there's enough dwell time that it's able to heat through the board so that the solder flows down around the component lead. All right, and then the last thing that we need to do on this is just to trim those component leads off. So just come in like so, cut those off flush, and we're done. And on to the next capacitor. Okay, the second capacitor is over here, and I'm actually going to add a little bit of solder to the board before we desolder. Sometimes on these connections there's just not much solder, and it will actually help to desolder by first adding a little bit of solder. That just fell right off the board there when I heated the second connection. Like so. And it looks like, yep, both of the holes are completely clear. There and right there. So again, these are plated through holes. You can see there's a trace that comes up on this side, there, and then on this side, this one has a trace that continues on. This second solder connection does not have a trace on this back side, but it is a plated through hole in both locations. Plated through holes are very common, but again, a vacuum desoldering tool is really the best way to remove components on boards like this. So we'll take the replacement capacitor and just drop that right in the board like so. There. This gives the leads a little bit of a bend outward. Holds the component flush down to the board. All right. And like so, that capacitor has been installed and this board is done. The second circuit board has a shield on both sides of the board. I've removed this bottom shield because we only need access to this portion of the board right here. We don't need to reach in from the top. These capacitors will just fall away from the board. So I'll get these next two changed out now. Alright, on the second circuit board I've removed the two capacitors that were in this corner. You can see them here. The old capacitors over here and our new replacements. Now the replacements, turn the circuit board like so. I can't drop them in just with this cover on here like this. I need to trim the leads just a little bit because these won't quite fit down in there. So just shorten the leads up a little bit first. So just trim the leads a little bit, and that should allow us to drop the capacitor right in place. Like so. And I'll do the same with the second one, just shorten the leads up. Alright, so solder connections are complete, capacitors are in place, and we'll just get those leads trimmed up. And like that, we have new capacitors installed, and this will be good for the long haul. So the last thing I like to do is to remove the flux off the circuit board where we've done our solder connections. So I'll do that now here and on this circuit board over here as well. I just have some flux remover on a heavy-duty paper towel. Sort of wipe that off there. Those connections look really good there, no problems. And also on this circuit board where we did the capacitor right here, so that looks nice and clean there. And on the other side over here, yeah, looks nice and clean. So with those new capacitors on there, those circuit boards are good to go for the long term. So the next thing I need to do is get this cover reinstalled. It just goes on the back side of this board right here. Alright, let's get these circuit boards put back into the network spectrum analyzer and see how it functions. Alright, I have the two circuit boards reinstalled in the Hewlett-Packard 4195A network spectrum analyzer. So let's power it up and see if it works. And no problems. So we are set and up and running. So this unit should be good to go with those new capacitors installed. If you enjoyed this video, don't forget to give a thumbs up. And if you haven't subscribed to this channel, now would be a good time to do so. So until next time, goodbye.